All right, so greetings from the East Coast of the United States. I'm just not quite in Maine, but I'm south down in North Carolina. So I'm from, my name is Dr. Justin Martin. I'm from Wake Forest University School of Business, and I'm going to be talking to you this morning about using machine learning models for predicting emergency medical service demand, both in time and space. So this study was completed in collaboration with an EMS agency in Mecklenburg County, North Carolina, and they're responsible for serving the entire county. And what really inspired us to conduct this research was not just the gaps in the literature at the time, but also an interest in working with an actual EMS agency to develop a practical model that could help them to improve their forecasting efforts. And so when we think about EMS in the most traditional sense, essentially emergency medical services, it's a critical component to delivering of urgent medical care to communities. And these agencies tend to be either, it can be a public service provided by a municipality, or they can be a private organization. But at either rate, they provide out-of-hospital acute medical care and transportation to patients. And their primary goal is to effectively allocate ambulances and the personnel required to sufficiently cover a geographic area and minimize the response time in doing so, especially to higher priority call requests, such as things like cardiac arrest and stroke. To achieve this goal and to serve the population of their service regions, EMS managers and dispatchers continuously study the frequency and distribution of incoming call requests that they then use to establish their resource deployment plans, which specifies the number of ambulances and emergency response personnel. So these are paramedics and EMTs that may be required for future periods. So in simple terms, the goal of minimizing their response time is achieved by matching supply to demand. So the supply of their resources to the demand in the service area. And in an urban setting, such as a city or city area, this is extremely difficult as the demand for EMS is very dynamic. It fluctuates based on the time of the day, and also spatially based on the time of the day and the day of the week. As an example here, we can see a map of high priority calls that occurred. This is from our data set on August 20th, 2016. And these are calls between 10 a.m. and 1 p.m. So 10100, 1300. Along with this is also showing the ambulances that respond to those calls. So the calls that occurred are shown in red, and the ambulances that responded to those calls are shown in blue. Now, while the locations of the ambulances are not matched up perfectly one-to-one, we can see that the placement at the time of the call is fairly close. So this just clearly illustrates the never-ending chess game that dispatchers have to play throughout the day. It's also important to note that EMS demand does exhibit some predictable patterns over time, which makes it a good candidate for a machine learning type problem. Now, there's been several studies conducted in the area, the field of EMS, addressing a multitude of issues. And as you can see here, issues or problems related to locating ambulances, dispatching them, relocating them, the interactions between ambulance agencies and healthcare systems. And within the area of forecasting specifically, several studies have examined and proposed different models for call demand forecasts. However, very few have actually incorporated the spatial component of demand, and very few have actually produced spatially distributed forecasts, which again was an inspiration to this study. Furthermore, when we consider all the various location and non-location based models that have been developed throughout the EMS literature, at a practical level, they're all dependent on one central input, and that is call demand forecasts. What I mean by that is that ultimately, to decide where we need to place our ambulances and how many ambulances we need, for example, in terms of the deployment problem, well, we have to have good forecasts based on historical data to know, basically how many, the supply side problem, how many ambulances do we need and where do we need to put them. So when we say call volume forecasting, we define that as predicting the calls that we're going to receive. So actually 911 dispatch calls, again, in different countries, 911, maybe 999, those types of calls we receive in future periods. And we forecast it at varied levels of time and space, typically using historical call response data. And so the prevailing industry approach, the trend, is to use simple time series forecasting methods such as moving averages. And believe it or not, I work as an EMS consultant. I can tell you right now, today, most EMS agencies across the United States are using some form of a time series method, simple moving averages or some proprietary type moving average formula that's built into their software to actually predict future call volumes. And so they use what's called CAD, which is computer aided dispatch software, to accomplish this. And these methods are historically have been very effective for strategic and tactical capacity planning. So when we're talking like long-term planning, like how many calls are we going to get next week or next month? We'll talk about why that's not that difficult to predict in just a moment here, but essentially those methods have been effective for broad stroke planning over broad geographic areas and longer periods of time. However, the accuracy of those methods does decrease significantly in the short term when we're talking about hourly or sub-daily, so kind of an hour range, when we're actually trying to make predictions at finer levels of spatial granularity. And so that's the big challenge here. Essentially, as we get more granular, forecasting accuracy gets a lot more challenging to hit reasonable numbers. So one of the previous studies that was a major inspiration of our work and served as something of a benchmark was a study from the same EMS agency and the same service area where spatially distributed call predictions were produced. And essentially, they took a very simple approach where they laid what's called a fishnet diagram. If you've ever done any geospatial analysis, a fishnet diagram is basically even spaced blocks. They laid this square grid pattern over the county, and they coded historical calls based on which calls fell into which areas, and they used that information, that data, to train their model. And the major issue that they encountered was that of granularity. Essentially, how granular should we go? Right? Ideally, you want to go as granular as possible. This idea that I want to know as close to the exact area that a call is going to occur, but practically that's not very realistic. And by drilling down to this granular level, they inadvertently created what's called a zero inflated distribution, where if I drill down to really granular levels, I'm going to get to a point where most of my grid locations on the map are actually going to have zero calls historically. And so you train a model just on zero, and that really isn't very helpful. It makes the model accuracy very, very hard. So just discussing accuracy and the distribution here, we can look at this example on the right where we can see that there's 23 calls that are received over this is a 3-hour period here that I'm showing you on the right-hand side. And within that, only 12 out of the 40 grids have calls. So that means 28 out of the 40 do not have calls. And so with that, our prediction accuracy is essentially, right, we get 30% with calls and 70% without calls. And so that's a very difficult that's a very difficult data set to use when it's zero inflated of that manner. So our primary objective was, well, how can we formulate a forecasting framework that utilizes machine learning methods as that previous study did, but we want to generate daily, hourly, and spatiotemporal calls at a degree of granularity in time and space that is both practical and actionable, and also want to avoid that zero inflated distribution issue by drilling down to too fine of levels of granularity. So we surveyed a wide variety of models, including support vector machines, XGBoost, ensemble methods, and we came to this proposed framework after many tests and surveys, where we start off with a feature selection approach using an ensemble-based decision tree model. This is called Baruda. It's a very popular feature selection approach that exists today. It's available in packages for R and Python. And we used forecasting, we used a multi-layer perceptron artificial neural network. And then we conducted our spatial segmentation using k-means clustering. Now, since data points are grouped together based on relative proximity, k-means is a good approach for creating spatial clusters. And for that, we used latitude and longitude coordinates of our calls to actually create these clusters. and then allows us to very quickly and very easily create spatial clusters that correlate directly with population densities and associated call volume densities, which is important in this type of data. So if we're looking at our data set that we had a very large data set of 8 years worth of call response records. So again, every time a 911 call was placed, basically we had that record, and we filtered down and focused on the high priority calls, which requires the fastest response time. So that was a data set of 633,000. Those call volumes were aggregated at daily and hourly level. And then we had a set of candidate data features, like attributes essentially, representing temporal features. So year, season, month, week, day of the week, day, and hour. We also added in some other features to account for lag values, basically. So this is a time series problem. So in order to have a good picture of the time series horizon, we added in lag values for daily call volumes, hourly call volumes, and then we also included these lag variables in the artificial neural network to create these rolling window predictions, which is very important when you're doing time series. So this here is just a snapshot showing you the average high priority call volume by day of the week in our data set. And what is very stark here in this data set, you can see, is this nice curvature, really showing you the volumes throughout the day and for the different days of the week. And it's important to recognize that we have these very stark, very stark temporal and seasonal behaviors that are represented in our data. And so those have to be represented in our input features to properly train the machine learning model to identify these trends. And so obviously this being averaged creates very smooth data, but not being averaged isn't as smooth. But it's just an important thing for us to point out. So we conducted, as I mentioned, feature selection using Baruda, which is a very cool algorithm. I say it's really a cool approach. Actually, it's very simple. Basically, what it does is it's used to identify which features are relevant to our problem. And so for each candidate feature, so if we have a particular feature we're looking at, what Baruda does is it creates a shadow feature of that original feature, basically by shuffling the original values of that attribute and creating this new shadow, what it calls a shadow feature. So for example, if it has the value of max temperature for a day, and that's equal to 72 for day 1, 64 for day 2, and so on, those values would be randomly shuffled. And so this shadow feature maintains the same mean and standard deviation of the original feature, yet it should not have any significant correlation with the original variable or with our target variable. In this case, we're trying to predict call volume. And it shouldn't have any correlation because it's been created through a random process. Now, after creating these shadow features for the original feature, Baruda compares the predictive power of the original feature against that shadow feature. And if any of the original features have a lower prediction power compared to their corresponding shadow feature, basically they're less powerful, to make predictions than random chance, then obviously, that is not an important feature. So Baruda labels that as not being important or relevant to the problem because it's no better than random chance. And so this is a very useful approach to conduct feature selection, which if you've ever done any machine learning, can be a very challenging process as far as your data processing goes before training your models. We then moved on to our forecasting with multi-layer perceptron artificial neural network, and we evaluated performance of that against several other common industry methods, such as ARIMA, exponential smoothing, and then a proprietary industry moving average method that we got from our client. The data from 2010 to 2016 was used for training and validation, and then data from 2017 was used for testing our model and benchmarking it. We went through an exhaustive process of tuning our hyperparameters and running various tests on using different feature sets and things of that nature to make sure that we were keeping everything nice and organized there. And our performance metrics that we used were a mean absolute percent error and mean absolute deviation, which there's a lot of debate on which performance metrics are the best to use with this kind of data, but that is really the industry standard. So we wanted to be able to compare our approach apples to apples to the industry standard. So looking here at our results across the various the various daily call volume forecasts. Multi-layer perceptron did beat out the other methods. This is just a sampling. We had other methods that we looked at as well, but this is the sampling of the top three. And you can see here comparing it to Holtz-Winter's triple X spatial smoothing. It performed just a little bit better, and same thing with ARIMA. Now, when we scale down to the hourly call volume level, where EMS call volume levels tend to be very stationary and repetitive in nature, going back to that average kind of smooth graph that I showed, the use of traditional time series forecasting techniques such as moving average and exponential smoothing does tend to be, very, very good here. So we can see here that the industry method that our client was using did actually outperform an artificial neural network, but only slightly. Whereas ARIMA and exponential smoothing really just fell short compared to those other two methods. Now, when we drilled on spatially, this is a very, very different story because the data is not going to be as stationary. It's not going to be as consistent. It's going to be much more complex. And so that's where a machine learning model should do better. And so we incorporate the spatial component of demand, as I mentioned before, by using k-means clustering to create these spatial clusters. And then basically whatever cluster the historical calls fell into, we labeled that as a feature, right? And then included that in our model. And it's important to understand a practical level of granularity is required to produce operationally valuable demand estimates that can support real-time dispatching decisions. So we worked closely with our EMS agency to identify what they believe to be the right level of granularity. And we also used what's called the elbow method, which is a method that aids in identifying an optimal or near optimal value for K in a k-means model, basically by fitting the model with a range of values for K and then calculating the average within cluster sum squared error. This is a very well documented method you can look up if you're not familiar with it, but it helps you to identify what is an optimal level of granularity for spatial, for clusters rather, in a clustering model. And so we applied that here and matched that up with what we were, what we discussed with our EMS agency as far as the practical level of granularity. And that got us to basically a range of 7 to 9 clusters. And so this here you can see is when we fed our data into the clustering model, this is how it segmented the county. And when we showed this to our clients, they're actually very shocked at how stark and how clear it delineated the different sectors of the city. So for example, that light blue section of the city is actually the center of our city in our county. And a lot of the borders of the clusters correlate very closely with major interstates and highways that run through our county. So that was just an interesting finding right off the bat with these clusters. But again, we used whatever cluster the calls fell into as a feature encoded in our model, and then we ran our machine learning models using that. So if we look at just the 9 cluster configuration, which is the one all the way to the right here, that's the most granular, this was the results for that. So again, we looked here at ARIMA, Holtz-Winters, this method that's used by our EMS agency, which is a moving average time series approach. And then off here on the right is our multi-layer perceptron artificial neural network. And so I'm showing their mean absolute percent error and mean absolute deviation. And so when we compare the performance of the spatially distributed hourly forecast against the benchmark method, which is that MHF, MEDIC hourly forecasting method, the MLP model consistently yields lower estimation error across all the spatial clusters in terms of MAPE, and then very, very close in terms of MAD. Now, to help visualize the distribution of these errors spatially, let's take a look here at a map. So this is here a map of Mecklenburg County. And so what we found was that our MLP model predictions are found to be more accurate for clusters containing relatively lower call volumes. So clusters that had less than 10% of the total county-wide call volume. So geographically, these clusters represent suburban and rural areas. And then both approaches were shown to produce higher error values in clusters containing greater than 10% call volume and population densities. So these clusters represent urban centers in the county that have a greater concentration of mixed-use development, multifamily housing, and commercial buildings. These higher density clusters also encompass or are adjacent to many of our central hospitals and emergency departments. And so according to practitioners, at any given time, and we know this just from history, at any given time, we have multiple ambulances that are located in and around those areas. And so really the major challenge for our EMS agencies is deploying and planning for those rural and suburban areas, right? Making sure we have exceptional coverage in those lower volume areas. Therefore, a forecasting model such as the one we have here, the artificial neural network, that produces more accurate spatio-temporal call volume estimations than the current industry method is really critical. And it gives us, where we have that advantage with that model in these lower volume areas where the need for accurate predictions is far greater. So moving to just some conclusions, and I'll leave some time here for questions. Given a systematic feature selection and hyperparameter model tuning, we found that MLP artificial neural network model outperforms consistently the other methods at a spatially distributed hourly level. In terms of MAPE, MLP significantly outperformed the traditional time series methods across all of the clusters, and the details are in our paper, which is published in the Operations Research for Healthcare Journal back in 2020. So you can, if you're interested in looking at more of the details behind this, you can reference that paper. But it definitely gave us, some practical implications, given the need that practitioners have for more accurate call volume predictions. And so I now work as a consultant in addition to my academic duties with this agency, and we've actually implemented many of these ideas into their daily operations. So anyways, that's my presentation. Thank you for your time. And if you have any questions, I'm available to discuss anything.